The name of this video is Energy Continuous. Suppose we have a continuous charge distribution with volumetric density small ρ in a region capital omega in space, where any point capital Q is a source point in this region of space capital omega. We want to find an expression for the electrostatic energy for this specific problem. So let's remind ourselves what was the electrostatic energy UE for a discrete set of point-like charge particles in space. For a discrete set, we know that this has to be equal to 1/2, not to forget the half, times the sum for index I, which goes from 1 to capital N, of Qi, the IF charge, times the electrostatic potential due to that charge, capital V, index I. This is our definition, and I'm not going to spell out again Vi, we found it in a previous video. Remember the factor of 1/2. This is for a discrete distribution. We are using a sum and discrete values for the charge, which is point-like, and the electrostatic potential associated with it. How can we find a similar expression, which of course will have to involve integrals instead of sums and non-discrete quantities, for a continuous charge distribution? The procedure is the inverse of what we have done in the previous video about energy discrete continued. So what we do, we split this region capital omega, which is an object in space, in an infinite set of infinitesimal volume elements, where each of these tiles, you need to think about it as an infinite is in 2D, the representation which I do on the board, but in real life is a 3D quantity. So this 3D quantity is an infinitesimal volume element with volume dV, centered around the point capital Q. Okay? So we know that this element has a volume dV. Since there is a density ρ at point capital Q, the infinitesimal charge dQ at that point is ρ at point capital Q times dV. Not to confuse ourselves between this V and this V, let us rewrite this dV as d of a generic vector r, which represents position, with respect to point Q, so we don't forget that knowledge, power of 3, because of course it's a volume, so it's meter cube, okay? All right, so this allows us not to confuse ourselves with these V's. So this object here effectively behaves as a point-like charge. You've seen this before. So I have an infinite set of point-like charges. What I do next, I define an infinite boundary, as we have done in our previous video, this dashed line. That is, the region capital omega right now resides in my laboratory, in my lab. I cut it with a very special knife into this infinite set of infinitesimal volume elements, all attached to each other, and then I spread them all the way away from my lab behind this infinite boundary. That is, this element, I bring it over any path, all the way here to the behind the infinite boundary. And similar for all the other elements. This I bring it here, this one I bring it here, and so on for all this infinite set of elements. Now, after this first step, so this first step goes outside, okay? All these particles resides now in a region of space where they do not interact with each other and they do not interact with anything in the lab. So we are basically in the same configuration we used for a discrete charge distribution, okay? We are exactly in that configuration. And now we do the opposite procedure, which is to bring one by one these dQs, which is an infinite set of them. So this is the dQ here associated with this volume dV, and these dq's are everywhere. So one by one, I bring them back following any path I want, as long as I bring it back exactly from where we started, in the neighborhood of the point where we started. And I do the same thing for all these particles, dq's, which are point-like, as long as I bring them back always to the very same point from where we started, okay? So in blue, I've done procedure 1, which is to go outside this boundary, and then 2, in green, to bring them back in to the same point where we started. So we do sort of a collage, which allows us effectively to reglue together, to recreate exactly this object, capital omega, with its own geometry and shape, and with its own volumetric distribution rho of q. Okay, so we need to recreate exactly the same structure. And the electrostatic energy is what glues together this object, like our body is glued together by electromagnetic energies more in general. And so this force effectively is the glue which keeps us together. Okay, so that's what we do. We broke it in pieces and then we bring it back and we glue it together by means of an electrostatic energy. Now we want to do a mapping. We want to do a mapping from this discrete distribution to a continuous distribution. So we want to do a mapping. And what is the mapping which allows us to make to go from a discrete to a continuous? It's rather simple, the mapping. So the mapping is, of course, 1/2 remains, because we are using the same procedure, so it gets mapped to 1/2. What about the sum? The sum for I, which goes from 1 to capital N, gets mapped to an integral, a volume integral in capital omega. What about Qi? Qi gets mapped to dq, which is rho at capital Q, dr capital Q cube, which is dV. And finally, Vr gets mapped to V, capital V upon capital Q. So this is our map, where here we have the discrete case, and here we have the continuous case. Great! With this mapping in mind, we can readily generalize this to this continuous charge distribution. UE is equal to 1/2 remains 1/2. The sum is the integral over capital omega. Qi becomes dq, which is rho upon capital Q, times Vi, which is capital V upon capital Q, integrated over dr capital Q cube. Excellent. So we began from this discrete charge distribution to obtain a continuous charge distribution electrostatic energy. Excellent. There is one last little caveat, and again, caveat in Latin means warning, and it's very much used in physics, that's why I use this word. So the last little caveat is that this integral, which is done only on the region capital omega, which is where rho of capital Q is defined, we can extend it. We can extend this integral to a region capital omega infinite, which includes capital omega. So capital omega is less than capital omega infinite, where this capital omega infinite is basically any region which extends all the way to infinity. So it's basically this boundary. This is my region capital omega infinite, and it can have any shape you want. It could be a sphere, it could be whatever you want, as long as it goes all the way to infinite in space, the entire universe. This is the entire universe, okay? Of course, in experiments, sometimes the walls of the lab are already shielded somehow. We'll see shielding later on, and so that's enough to say that that's our universe. So it depends, of course, on the experiment that you're trying to do. But by means of this extension, we know that rho is equal to 0 at any point q prime in this region outside capital omega. Only in this region there is an object with a charge. Outside we have vacuum. The integral over something where rho is 0, of course, does not contribute, so we can extend this integral to be 1/2 is equivalent to the integral over this super region, the entire universe, omega infinite of rho, which is 0 outside, so it gives the same result. Great. This is very important for an extension which we will do in a few minutes. So to summarize this video, we wanted to find an expression for the electrostatic energy for a continuous charge distribution. So we start with an object, capital omega, which has a certain shape, geometry, with a certain volumetric density rho. We partition it in an infinite set of infinitesimal cubes, each of which is characterized by a point-like charge dq. We spread all these charges behind an infinite boundary, infinitely far away, and we follow the inverse procedure now, what we have done to find this expression for discrete charges. Now all this effectively here, there are a discrete set of charges, we bring it back exactly following an opposite path, which can be whatever path we want, but as long as we bring it back to the same point where we started, we reglue together with electric energy this object, and by means of a simple mapping, we can find the integral form for the electrostatic energy in this case, and then we generalize it to the entire universe, where outside is capital omega, in capital omega infinite, in the region, in the negative space between capital omega infinite, the universe, and capital omega. So here, not here, here, the charge is 0, distribution, and so we can generalize to this entire universe. That's it.